now what I want to do is a simple exercise where we would like to compare the capacitor model and the diffuse AA model. Okay. So, this is what we had derived earlier, that is d psi by dx is equal to delta psi divided by delta is equal to sigma star divided by epsilon naught epsilon r, okay, where delta psi is the potential drop between the plates. Okay. Now, I would like to take the psi is equal to psi naught exponent minus kappa x and d square psi by dx square is equal to minus rho star divided by epsilon, right. This was the basic equation that we used for obtaining how the potential varies with separation distance, right. That is the right. Now, I would like to use these expressions and then express this in a way I can compare with the capacitor model. Okay. So, for that what we will do is, okay, so I have written an expression here, okay, which tells you the sigma star, which is the surface charge density, okay, which is the surface charge density that we had in the capacitor model, right. And this rho star is the charge density, but that is charge per unit volume, right, in this case. Okay. Right. Now, if you assume, okay, if you assume that I do not have any other added electrolyte, I only have the charges because of I only have the counter ions that come because of the dissociation of charges on the particle surface. Okay. Then what I can do is I can say that because of the electroneutrality, okay, I can say that the charge density, okay, at the two faces must be equal. When I say two faces, one I am talking about the charged surface at the two phases, okay, it is not two phases, two phases, okay, because of the electroneutrality, the charge density in the two phases must be equal. When I say two phases, one is the charged surface and the counter ion subphase. Okay. The other way of saying the same thing would be, so the total charge, okay, the total charge contained in a volume element of a solution across, so let me put it this way. Okay, let's say this. Okay. So, I can define sigma star, right. Then what you do is I consider the total charge that is contained in a volume element, okay, and I am going to count all the ions that are present from the wall to a infinite distance away from the wall. Okay. The total charge that is contained, okay, determined in that way must be exactly equal to the charges on the particle surface. However, they should be opposite in sign. Is that okay? So, we are talking about in this case. So, imagine that now I have a diffuse double layer now. Okay. We will come back and ask. Okay. When one of the phase contains diffuse layer, that means this is a charged surface, okay, and I have a diffuse layer. When one of the phase contains diffuse layer, the total charge contained in a volume element of a solution across the cross section, okay, extending from wall to infinity, must contain the same amount of charge, although opposite in sign as the unit area of the wall contains. Okay. Yeah, so that is what this expression essentially tells you. Yeah, you have a question. Yeah.
No, I wanted to ask, sigma star is on the particle and rho star is.
Yeah, so yeah, that's a good point. So sigma star corresponds to the charge density of the surface. Okay, if I have a charged surface, okay, so what we defined is sigma star was q divided by a, right? The total charge on the particle surface divided by area. That is how it was defined. Okay, and in this case, rho star is a charge in the solution. So we are talking about equating the charges on the particle surface and the charges in solution. Okay, and because of the fact that the electron neutrality, must be preserved, the total charges that are in the solution on the particle surface should be same as the charges in the solution. However, they should be of opposite sign. Okay, think a little bit about this. We can discuss this further as well. So now, I have rho star. I can, instead of sigma star, instead of rho star, what I can do is I know that rho star divided by epsilon, okay, is d square psi by dx square, right. So, I am going to replace for that. Instead of rho star, I am going to have d psi by dx, and I am going to have epsilon that comes here, and there is a minus here, it becomes plus, right. So, therefore, sigma star is epsilon 0 to infinity d square psi by dx square into dx, okay. And I would have to sum up all the charges all the way from distance is equal to 0 to infinite, right. Therefore, sigma star, if I integrate this, I can write this as sigma star is equal to epsilon into d psi by dx at infinity minus d psi by dx at 0. Okay, that is at the surface of the charged body, okay, and that is at a distance very far away from the charged surface. Okay. And we know that d psi by dx at infinity is going to be 0, because we know that psi itself is 0 at x is equal to infinity. Therefore, the first term is going to be 0, then you are left with epsilon times 0 minus d psi by dx at 0. Therefore, sigma star is minus epsilon d psi by dx 0, and because we know that the potential varies falls in in an exponential way, I can get what is d psi by dx at 0. Therefore, d psi by dx at 0 will be psi naught exponent minus kappa x times minus k, right. Is it okay? And because for x tending to 0, this term becomes 1. So, I have minus k times psi naught. Okay, therefore, sigma star, which is equal to minus epsilon d psi by dx at 0, will be equal to epsilon kappa psi naught. Okay. And therefore, I can rearrange this to get sigma star is equal to epsilon into psi naught divided by kappa inverse. And if you look at the capacitor model, the expression was sigma star is equal to epsilon delta psi naught divided by delta. Okay. So, we are able to express sigma star obtained from the Debye-Huckel approximation in an equation which is analogous to the capacitor model. Okay. Okay. So, what you can infer from this is these results, they essentially show that the diffuse double layer at low potential, you can think about it behaves like a capacitor model. Okay. However, the separation distance is replaced by k inverse, right. Instead of delta, you have kappa inverse. But of course, this model captures the some really important features. For example, the distance over which significant potential exists decrease with increase in the electrolyte concentration. Okay. What I mean by that, if I look at this expression, what do you understand by this statement? The distance at which the significant potential exists decrease with electrolyte concentration, right. So, if I look at these expression, okay, of course, the if I go to a very far away distance, potential is going to be 0, right. Now, what is important when you worry about electrical double layer interaction is that when the two surfaces, charge surfaces come closer, if the potential, okay, when they approach, if the potential is very high, that means the repulsion is also going to be higher, right. So, if I look at a particular, okay, let us look at this potential, okay, which is this potential, right, it occurs at maybe separation distance of 10 nanometer. Okay. Let us go back and look at a same potential occurs at a much lower separation distance. Okay. The same potential occurs at maybe something like whatever 3.5 nanometer or something like that. Now, if I go here, the same potential occurs at even lesser separation distance. Okay. That is what the first statement essentially means. The distance over which significant potential exists decreases with increase in the electrolyte concentration, right. That was actually demonstrated by here, right, because this is a case where the electrolyte concentration is changing, right. The electrolyte concentration is changing. When the electrolyte concentration is 0.001, a particular potential occurs at 10 nanometer, but the same potential occurs at a lower distance when I have a higher concentration of salt. If I go for even higher concentration of salt, the distance at which the same potential exists even decreases, right. That is the first statement. The distance over which significant potential exists decreases with increasing electrolyte concentration. And the second point, the range of electrostatic potential decreases as the valency of the ions in the solution increases. This is right, that you can draw that from the second point. Sorry. Can I make another? I am going to read that again. Okay, the range of electrostatic potential, decreases as the valency of the ions in the solution increases. So, there, I mean, now you have a statement about the range of interaction. Okay. Now, the range of interaction, electrical double layer interaction, essentially depends on how does this potential vary with distance. Okay. If the potential falls off steeply, okay, the range over which the electrical double layer interactions become important is smaller. Okay. However, if you have a case where the potential decreases more gradually, that means the range over which the electrical double layer interactions are important is or the electrostatic interaction become important over a larger range of separation distance. Do you get that point, or do you have to explain?
1 by k is the range over which
Yeah. So, you can think about, yeah, you can in a way think about k inverse or 1 over k as a distance over which the electrical double layer interactions are become important, right. If you go by that, okay, so the more the kappa inverse is, more would be the range, right. Now, because I am able to decrease kappa inverse by adding a higher concentration of salt or by increasing the valency of the ions that I have put in, therefore, kappa inverse is going to go down, therefore, the range of over which the electrical double layer interactions become important is also going to go down. Okay, that is the point. Anyway, think a little bit about it. So, that is about what I wanted to speak today. So, what we will do in the next class is to look at more general solution, Okay. Instead of looking at linearized Poisson-Boltzmann equation, we will just look at a more general case for a symmetric electrolyte, and then we will try and look at how does the potential vary with separation distance, and then discuss again the implications. Okay.